Okay, so here's our lesson for today. Please make sure that you are using Cami and write down your name on the page. Okay, so throughout this video, remember that I do expect you to be pausing and playing often so that you can kind of take a step back and try to solve the problem yourself first, and then check with my answers to see if you got it right. And you can always skip through the video as I work through the problem. If you do it on your own and then you decide, okay, like I think I got this, I just need to check my work, you can kind of skip through the explanation. And if you realize that you do need more explanation, then you can just go back and rewatch that part of the problem. Okay, so just be really smart with how you use this video. I'm going to go relatively quickly just because I don't want to take up any more time than is necessary. So please remember that it's your responsibility to pause. Okay. Today we're going to learn something new called the addition rule. So I'm going to kind of just incorporate it into the problems itself. So I will introduce it later on whenever it becomes relevant. But just keep in mind that this is the biggest part of this lesson, is learning how to use the addition rule and when to use it. Okay, so number 39, we have a popular restaurant in the mall. Hold on, Marley, lay down. Thank you. Sorry, guys. You guys want a dog? Come get Marley. I'm just kidding. A popular restaurant in the mall has conducted marketing research on 4 new salads it is considering putting on the menu. The percentages of study participants in various age categories and their salad preference are shown in the table below. It states that salad preference was found to be independent of age, which means that somebody's salad preference did not depend on how old they were. There was no trend in that way where older people liked feta and younger people liked barbecue, right? There was not a trend in that way. So just remember that the 2 things we're looking at are various age categories. So age is here. We have under 25, 25 to 34, and so on, right? So you want to look very carefully at those. And then the other category is their salad preference. So here we have feta cheese salad, barbecue chicken salad, Asian ginger salad, or chopped cob salad. Okay, and these are the percentages of people who voted that they liked those salads. So what I want you guys to do is practice finding the probabilities inside of these boxes. So these boxes show us, like this first one would show us what percentage or what probability does somebody under the age of 25 like feta cheese salad. The way we're going to find this is if we multiply their decimals. So this one would be 0.36 times this one being 0.1. So if we multiply those 2 together, that's going to give me the probability that somebody who is under the age of 25 likes feta cheese. All right, so please try to multiply those 2 probabilities together. You should get 0.036. And then if you also wanted to see it as a percentage, you would move the decimal to the right 2 times. So 3.6% of all of the people surveyed who are under 25 years old like feta cheese, or they prefer feta cheese on their salads. Okay, so you guys can do this for every single problem here. What I would do is convert all of the percentages to decimals. So then it makes it a little bit easier to multiply. This one is also 0.14. Be careful, 8% is 0.08 because it's 8 hundredths, so it's in the hundredths place. Oh, not 6, sorry. This one's 6 hundredths, and then this one is 5 hundredths. This one over here, 60% will be 0.6 or 60 hundredths or 6 tenths. Okay, and then 0.1 again, and then 0.2. All right, so go ahead and multiply all of your probabilities to find what each of these are going to be. I'm going to go ahead and just start filling them in on my own, and then you can always pause right now and do them on your own, and then skip ahead to whenever I finish them, and then you can see if you got all the answers correct. Okay? So this one, 0.1 will be 0.014 or 1.4%. Okay, I definitely need my calculator for this one. So don't hesitate to use a calculator, right? Because I mean, I'm not perfect, right? None of us are perfect at this, so just do what you need to do to get your answers. Again, for going from a decimal to percentage, you could just multiply it by 100. So like 0.216 times 100 is going to equal 21.6, and that is the percentage of it. Okay, so that's how I get that. Or you just move it to the right 2 times. Either way. Okay. All right, so moving on, so we have 0.6 times 0.14, 0.084, which is 8.4%. 6 times 0.17. So this one has a bigger, gosh, Marley is so loud. I'm so sorry, guys. Marley, can you just freeze for a little bit? Just freeze. This will be 0.084, 8.4%. All right, so then this one, 0.08 times 0. Oh my goodness, hold on, guys. 0.08 times 0.6. Ah, there we go. I thought that was weird. I have no idea how I got that. I think I might have pushed add. All right, so then this one would be 0.048, 4.8%, 0.036, 3.6%, 0.03, 3%. Okay, and then actually I realized that the first row is the same as the third row because both feta cheese and Asian ginger have the same probability of happening within each age group. So those will be the same. And then the chopped cob is actually just double whatever the Asian ginger was because it is twice the percentage, you know, so it's 0.2 instead of just 0.1, 10% to 20%. So that can be kind of easy. You just double whatever is above. Sorry, guys. 3.4. I'm sorry. 0.34, 3.4%. To be careful with that one. Alrighty, so those are all the probabilities filled in, okay? So now we're going to use this table to answer the questions that follow. So again, please pause if you're not done with the table yet. Alright, so here it says, people who participate in the study will be randomly selected for face-to-face interviews. What is the probability that the marketing department will randomly select someone who is, so the probability someone is 55 and older and prefers barbecue? So first we have to see, all right, well, who is everybody who's 55 and older, right? So let's go and look here. So 55 and older are all of these people. This is 55 to 64, 65 to 74, and then 75 and over, right? So it's all these columns here. But I only want to know what amount of those people like barbecue. So the barbecue chicken is right here. So all these people prefer barbecue chicken. So I look at where they intersect. So this is called an intersection. So they intersect right here. So all these people are 55 or older in age, and they all prefer the barbecue chicken salad. I almost said pizza. I'm hungry, obviously. Pizza is way better than salad, right? But so those people are what the intersection would look like between 55 years and older and those who prefer barbecue. So what we have to do is add all of those together. So we have, so we can do percentages or decimals. I'll go and do percents. 4.8% plus 3.6% plus 3%. Okay, if you guys add that together, 4.8 plus 3.6 plus 3, you should get 11.4%. So 11.4% of the people who are 55 and older prefer barbecue. All right, so we're just looking at this population, only the people who are 55 and older. All right, so those are the people who we're looking at. So this here is called an intersection between those two things. It's whenever those two things happen at the same time, okay? So highlighted in red up there is called the intersection between these two things, all right? So now it says here, is the event you analyze in part A, I already told you, an intersection or a union? It is an intersection, okay? So part A is an intersection. And then the question says, how does the intersection of 55 or older and barbecue differ from the union of 55 or older and barbecue? Well, the union would be, what is the probability somebody is 55 and older or they like barbecue? All right, so I'm going to try to color code this for you. All right, so 55 or older are all, I'm going to go ahead and I'll leave the intersection there for now, but I might end up erasing that color. So 55 and older are all of these people right here. Okay, so all of these people in here. Yeah, I'm going to erase the intersection for now. Those are all the people who are 55 and older, or I could pick somebody who likes barbecue, right? So people who like barbecue, or they like barbecue, right? So I could either select any of those people in the green or any of these people who like barbecue. So all of these people like barbecue, but then you guys see here that I have to subtract out the probability that both of them happen. Otherwise, they're double counting this intersection right here, right? They are double counting this intersection. So in order to find the probability that we get somebody who's 55 and older or they like barbecue, we have to use what is called the addition rule. This is the addition rule. To find this answer up here, to find the probability somebody is 55 and older or they like barbecue, I'm going to add all the people who are 55 and older to all the people who like barbecue. But then what I need to do here, I'm going to go ahead and move this over real quick. Boop, boop, boop. Okay. But then what I need to do is subtract the probability that they are 55 and older and prefer barbecue. And it's because I'm only subtracting it in one instance, because if you see here, whenever it's highlighted in green and in blue, this is highlighted twice. So I need to subtract out one of the instances that both things happen, right? So the probability somebody is 55 and older, I can add together all of these. 14 plus 5, I'm going to get 19% of the people are 55 and older. I should probably color code that right. Hold on. Green. So green is the total amount of people who are 55 and older. We're at 19% of all the people. And then I'm going to add all the people who prefer to eat barbecue chicken, which is highlighted in blue there, is 60%. And then I'm going to subtract out the intersection, because look, this happens twice. So I need to subtract out just one of them, and I already know that the intersection is 11.4%. So I'm going to subtract out 11.4%. Now this is going to give me the probability that I randomly select somebody who is 55 and older or they prefer barbecue. So this is called a union. Whenever something has the word, I didn't mean to do that. Whenever something has the word or in it, you are using the addition rule. The addition rule. If you see the word or, that means you're calculating a union of two separate things happening. So then you have to subtract out the probability that they both happen at the same time. So whenever you do this, you're going to get 79% minus 11.4%. You have a 67.6% chance of selecting somebody from that sample, somebody who was surveyed, who likes barbecue or who is 55 and older. Okay, so this is just the introduction to the addition rule. I don't expect you to be a pro just yet, but hopefully you're able to logically wrap your brain around the fact of why we have to subtract the intersection. Okay. Okay, so we always have to subtract where they intersect so that we're not counting that data twice. That would completely skew our data. Okay, so we already did part C. I'm the worst. I always do that. We already did part C. So we already calculated it using the addition rule. Okay, so the addition rule is the probability. Let's go and take a few notes here. The probability. The addition rule is if I want to know the probability of A or B happening, so some event A or some event B, I need to add the probability of A to the probability of B and then subtract out the probability that they both happen at the same time. Or you can write the probability of both. And this is the intersection, where they would intersect in the area model and then it would be double counted. So that's why we have to subtract it out. So this is the addition rule, okay? The addition rule. So make sure you jot that down. Just use this space for notes since we already did the other stuff up there. This is so important. You will be tested on this on the exam, on an upcoming EST possibly. So please make sure you guys are pros at this, okay? This is what your Khan Academy will be on as well. The Khan Academy, I think, will really help you out with the logic of it. So hopefully you find that beneficial. Let's see here. What is the probability that a randomly selected person from the study is under 75 years old? So what is the probability we select someone who is under 75? Now there's a few different ways to calculate this. So you guys will see part E says explain how you calculated the probability of under 75. Well, I'm going to go ahead and do that as I do this problem. One way is to add all probability, so all ages under 75. Or I guess I should say, I'm sorry, add all probabilities of ages, because you're not going to add the actual ages, right? Probabilities of ages under 75. So if we do that, let's see here, all the ages underneath 75. So this one off to the right here, I'm going to go ahead and erase some of this stuff. This one off to the right here is everything that is 75 and over. So what we need to do here, I'm going to move this guy out of the way. What we need to do here is add up everything that is not 75 and over. So these are all the probabilities that we need to add together. So if we, whoopsie, nope, paste image, there we go. All right, so we need to add all of these numbers. Let's see if it lets me make it bigger. There we go. And this will end up giving me the probability of me finding somebody who is under 75. If we add all these together. So 36 plus 14 plus 17 plus 14 plus 8 plus 6. Okay? So here, if we add all those together, we're going to get that the probability of somebody under 75, take a moment to add all those together, you should get 95%. Okay? So now that's one way to do it. That is one way to do it. So the probability we choose someone under 75 is 95% of a chance. A different method is using something called the complement of the event. So the probability of under 75 is equal to the entire percentage of all the people minus the probability of somebody who is not. Oh, I wrote that totally wrong, guys. The probability of someone who is not under 75. Okay, so let's go up here and see what is the probability of somebody who is not under 75. Well, all of these people here are under 75. So the only people who are not under 75 are the people who are 75 and over, right? So we have 5% of people who are not under 75, 5% of people. So if we do 100%, all of the people minus the 5% who are not under 75, we get that the probability of people under 75 is 95%. 100 minus 5. Another way to do the complement the complement of the event, is to do 1 minus the decimal. So this side over here, these are the percents, but we could also do it with decimals. So if I say the probability of under 75 is equal to 1 minus 0.05. That would be the 5% who are not under 75. So the probability of being under 75 is equal to 0.95, which is equal to 95%. So either way you decide to do it, you should still get 95%. Okay? So that is what is called the complement of the event. When finding the probability that something will not happen, you are looking at the complement of the event. So not being under 75, right? So we had to use the idea that the probability of under 75 is 100% minus those who are not under 75. So here we have a problem. It says, show 2 ways to solve the problem below, then decide which way you prefer and explain why. The marketing department has interviewed people of all different age groups about the barbecue chicken salad, but now they need information about why the other salads are less popular. What is the probability that the next person randomly chosen will not prefer the barbecue chicken salad? So first you can add all other salad probabilities together. Okay, so if we want the probability somebody does not like the barbecue, we need to add the probability of feta, that they like feta, the probability that they like the Asian salad, and the probability that they like the Cobb salad. So again, these are just the salad choices here. So what is the probability that people do not like the barbecue chicken? Well, I got to add up all of these probabilities, all of them, okay? So the probability of not barbecue chicken is going to be equal to the feta being 10% plus the Asian being, actually I think the Asian was also 10%. Let's check. Yep, so fetas and Asian ginger are both 10%. And then the Cobb is 20%. So the probability somebody does not like barbecue is a 40% chance that somebody does not like the barbecue or does not prefer the barbecue. You guys could have also added together the decimals as well, and you still would have gotten 0.4, which is 40%. You would have done 0.1 plus 0.1 plus 0.2, 0.4, 40%. Same thing, right? Or instead of this method, or we could find the complement. Okay, so we can use the complement, which just means there's 2 different ways if we want to do decimals or percents. So I'll do percents up here and then decimals down here. So with percents, we would say the probability of not barbecue is equal to 100% minus the probability of barbecue, of people who do like barbecue. In decimals, we would do the probability of not barbecue is equal to 100, sorry guys, I'm tired. 1 whole minus the probability of barbecue. So with the percents, 100%, 60% of the people like barbecue. 60% if you go back up and look at our table. So that tells me 40% do not like barbecue or do not prefer it, right? The probability of barbecue is 0.6. 1 minus 0.6 is 0.4, which is 40%. So any way you do it, the probability of not barbecue is 40%. Whatever way you solve it, you should all end up with 40% each time. Okay? Here it is. It says, if the probability of an event A is represented symbolically as P of A, how can you symbolically represent the probability of the complement of event A? So it's asking us, how can we represent the probability of not A? There's 2 ways. with percents, it's 100% minus the probability of A. Or the probability of not A could be with decimals or with the whole one, right? 1 minus the probability of A. So this one would have to be in percent form. This one would have to be in decimal form. So whichever one you choose, you should still get the final answer being the same. That is the complement of event A is not A. Okay? All right, here's a new one, so make sure you guys pause before if I move too fast. Avery has been learning to play some new card games and is curious about the probabilities of being dealt different cards from a standard card deck. Help him figure out the probabilities listed below. All right, a standard card deck, first of all, has 52 cards. There are 4 suits. So the suits are clubs, spades, hearts, and diamonds. So there's an even number of each of those suits. So if I were to divide 52 divided by 4, I get 13. So there are 13 clubs, 13 spades, 13 hearts, and 13 diamonds. Okay, so that's some important information. We also know that cards have like kings, right? How many kings are in a deck? There's 4 kings in a deck. How many queens? 4 queens. How many jacks? 4 jacks. How many tens? 4 tens, and so on. So there's 4 of every number or every face card. Also like 4 aces, 4 twos, 4 threes, 4 fours, 4 fives, and so on. So let's go and talk about the probability. What is the probability of drawing a king from a deck of cards? Try it out on your own. Please pause the video and try to write me a fraction representing the probability of drawing a king. So there are 4 kings in a deck out of 52 total cards. So the probability of drawing king is 4 out of 52. Now you can convert to a decimal if you'd like, but you don't need to at this moment. The probability of drawing a queen, probability of a queen is also 4 out of 52. Because there are 4 queens in a whole deck. Now the probability of drawing a club is a little bit different because a club is a whole suit. There are 13 clubs in the deck. So there are 13 clubs out of 52 cards. So that's it for part A. Now part B says, what is the probability of king or club? Okay, as soon as you see this or, that is addition rule. As soon as you guys see an or in that sense where it's comparing 2 different things, this is the addition rule. Okay, so this means, let me go and move this over just a little bit. Not the arrow though. Oh my goodness. There we go. This means it is the addition rule. Okay, so the addition rule is the probability of A or B equals the probability of A plus the probability of B happening minus the intersection that those 2 things are the exact same thing, right? In this case, they would be the exact same card, okay? So here we have a king or a club. So A is the king, that's the A event, or the B is the club. So I'm going to put those in. So probability of king plus the probability of a club minus the probability of a club that is, we should write king first, of a king that is a club. So if there's 4 kings and there's 4 suits, you can assume there's 1 king that is club, 1 king that is spades, 1 king that is hearts, and 1 king that is diamond. And you guys could see this if you pull out a deck of cards. You can look for yourselves. So the probability of it getting just a king is 4 out of 52. The probability of pulling any club is 13 out of 52. The probability of pulling a king that is a club is 1 out of 52 cards. Okay, there's only 1 card in that whole deck that is a king and a club at the same time. So if you add 4 plus 13 minus 1, you get 16 out of 52. So you have 16 out of 52 chances to pull a king or a club out of that stack. Now that 16 includes the king that is a club, but the reason why we had to subtract it out is because it double counted it. Because it counted it here in the kings and it counted it here in the clubs as well. So we had to subtract it out one time just to show that it's not being double counted. So now it says, what is the probability of pulling a king or queen? Macy, stop. Probability of a king or queen. So once again, I see the or, and that tells me addition rule. Okay, so I'm going to go ahead and follow that a little bit. So this would be A or B. So it's the probability of A, which in this instance is the king, plus the probability of B, which in this instance is the queen, minus the probability of both A and B. So a king, that is also a queen. That's interesting. A king that is also a queen. Is that even, I don't know. Let's think about that. So the probability to pull a king out of the whole deck. I have 4 kings in the whole deck. I have 4 queens in the entire deck. How many cards in the deck are both a king and a queen? Are any of them? Is that even possible? No, it's not possible. So 0. 0 of them are both a king and a queen. So this is just a logic type of thing. So if we add all those together, let me make them a little bit smaller here. All right, too big sometimes. The probability of getting a king or a queen, we just add together how many kings and queens there are. So it's just 8 out of 52 cards are a king or a queen. Okay, so that one's it. That's that for that one. What is the probability of not getting a face card? So again, there are several ways to do this. I like the complement. The probability of not getting a face card, not face card, is equal to 1 minus the probability of a face card. Face card. So it says here, jacks, queens, and kings are face cards. So if there's 4 of each of those, how many total face cards are in the deck? There are 12 total face cards in the deck out of 52 total cards. So one way to do is instead of writing 1, we can write that as 52 over 52. That is equal to 1 whole deck of cards. 52 cards out of 52 cards is 1 whole deck. So if we were to subtract that, we're going to get 40 out of 52 of the cards are not a face card. Not face card. You just subtract out the face cards. So 40 out of 52 cards are not face cards. Now, that's about it for us today. So just a little quick recap. Addition rule. Addition rule is so important here today. If we have the probability of some event A or some event B, remember that the or is really what you're looking for the addition rule. This is equal to the probability of A plus the probability of B. And then we have to subtract out the probability that both of them are happening at the exact same time so that we are not double counting both of them happening. Okay, because each one is already taken into account in these probabilities. We also learned the complement of an event. An event. We'll call it an event A. Oop, that was kind of... An event A would be like the probability of not A happening is equal to 1 minus the probability of A happening. Or if you did percents, 100% minus the probability of A happening in percentage form. Okay, so those are the 2 big things that we learned today. So make sure that you do review them. Make sure you rewatch this video. Maybe try to look up some things on YouTube about it just to kind of solidify your understanding. But that's it for today, so make sure that you turn in today's notes.